Okay, welcome. Okay, so let's start. Let me share the screen. Can everyone see my screen?
Yes, we can.
Okay.
Yes.
Okay, so today we're going to talk about mathematical proofs. So, as a mathematician, the most important task you'll do when it comes to research is proving. And proving is basically taking a bunch of statements, a bunch of statements you believe are true. We call them axioms. And using these axioms, you build up theorems. Theorems. And the way this works is, imagine you're trying to make a building, and your base is the set of axioms, the set of objects or mathematical things that you believe are true, and you use those facts to make up new facts, and these facts are undeniable. So in this chapter we will try to learn how to prove. And when we say how to prove, is how to prove a theorem. A theorem is like a mathematical statement, something similar to what you learned in fundamental logic. But here the statements would be more important, they will be meaningful, and we will see how we can prove them. So, so now we're going to start talking about the set of integers. And the set of integers is basically all the numbers you naturally know. So it's all the negative numbers, -1, -2, -3, -4, and it's 0, and it's all the positive numbers, 1, 2, 3, 4, 5, 6, all the way up to positive infinity. And remember that these numbers are not rational numbers, they're just whole numbers, positive and negative. This is the set of integers. Now, we come to our first definition. Wait, is this our first definition? I think this is our first important definition. Yes, so if n is an integer, n is even if there is some integer k such that n is equal to 2k, and n is odd if there is some integer j such that n is equal to 2j plus 1. And we define even and odd integers in such a way. Naturally, we know that we can define even and odd integers in a way that is easier for us to visualize, that is the set 1, 3, 5, 7. But we have to define it in a way that is more complete. So if you define an even integer like this, and you define an odd integer like this, it becomes easy for you to decide if a given integer is odd or even. Or at the same time, it makes it easier for you to do things with any arbitrary even or arbitrarily odd integer. Now, why is this important? Why is this generality in mathematics important? It's important because if you remember from fundamental logic, we have quantifiers in our statement. So if you're trying to make up a statement that is based on that is true for all even numbers, you need to pick an arbitrary element from that set. But how would you do it if you have not defined what an arbitrary element looks like? So this is what an arbitrary even number looks like, and this is what an arbitrary odd number looks like. So every definition and every theorem is sort of serving a purpose to what you're trying to do in mathematics. So let's say we have n and m, and they're integers. And we want to prove that if n and m are both even, then n plus m is even. And if n and m are both odd, then n plus m is odd. If n is even and m is odd, then n plus m is odd. Now notice here, this is an if-then statement. And the way we would show that this holds is we assume the first part, and then using that, we say that this is equivalent to saying, or this implies the second part. And how can we do that? Let's look at an example. I will not do all three of these. I'll just do one of them so that you can understand. So let's say it's given to us that n is an even integer and m is also an even integer, then n plus m is also even. Now, notice what this statement is trying to say. It's saying that for any nm even integer, so you take two elements from the set of even integer, arbitrary elements, and you add them, and you get something that is also even. So we say, let n be equal to 2k for some k belonging to the even numbers. Let's represent this set by e. Sorry, never mind, not e. K belonging to the integers, because this is the definition of an even number. And m be equal to 2l for some l belonging to the integers. Now, notice what you did here. If you remember logic, this is just universal instantiation. And then what we do is we try to describe what n plus m is. Now, n plus m is equal to 2 times k plus 2 times l. But this can be written as, because of the distributive property in addition in the integers, this can be written as k plus l times 2. But remember that k plus l, since k is an integer, l is an integer, k plus l is also an integer. And hence, this is being written as an integer times 2. Therefore, we can say, that n plus m is even. So what we did here is we took two arbitrary elements. We assume that the given hypothesis is true, that is n and m are even integers. We took arbitrary elements from those sets, and then using some mathematical techniques that we know are valid, we proved that this part implies n plus m is even. And this form of proof is known as a direct proof. So if you have an if-then statement, so if P implies Q in a direct proof, you assume that this part is true, you assume P is true, and using the mathematical techniques you know, and then I'm drawing this arrow, but this does not mean implication. So this means this means implication. Using mathematical techniques we get Q. And this is the form of proof that is called the direct proof. So did everyone understand this? Are there any questions about this? Are there any questions about this in general? Because I did this with a lot of detail. I will not do the next parts with this much detail. I believe there are no questions. Guys, it would be better if you can speak up or at least write in the chat. So moving on.
Yeah, I'm hearing you.
Okay. Okay, so most of the proofs you will do will be in the form if P then Q. So it's better to understand mathematical statements and convert it into this form because it makes your task easier. You can think through if you know what P is and if you know what Q is. So let's try to do this in this one. This question: the area of the region inside a circle of radius r is pi r squared. How would we write this in an if P then Q form? Does anyone have an answer for this one?
If area is the radius of the what circle, then the area of the circle is pi r square.
Yes, that is correct. So we understood what we were assuming here, and from there we went to our conclusion. So if we wrote it in the form if P then Q, and the way to prove this would be we assume the given statements, and then we go to our conclusion. So let's do part 5, fundamental theorem of calculus. Let f be a continuous function on AB, and f be any function for which f prime x is equal to fx. Then this part holds. Actually, this is given in that form anyway. Like if you change let to if, this is pretty simple. How would we write this in an if-then statement? To do this, we would say that if x and y are integers, or let's say real numbers, let's say integers for simplicity, we would say that if x and y are integers, then e to the x plus y is equal to e to the x plus e to the x times e to the y. So the simplest form of proof is the most obvious one. Assume P is true and then produce series of steps, each one following from the previous ones, which will eventually lead to Q. This proof is called a direct proof. So this is the basic outline of the proof. It's supposed that P is true, then we argue, and then we get to Q is true. I like to think of proving something in mathematics as to being a lawyer in a courtroom where I'm trying to look at the jury and trying to convince them that, okay, we know this, and we know from this that this is true, from this to this is true, therefore Q is true. So if P is true, then Q is true. So always, when you imagine yourself being a mathematician, think of yourself as a lawyer, trying to prove something in the court of mathematics. Let's look at the next definition. Let A and B be integers. The number A divides the number B if there is some integer Q such that AQ is equal to B. If A divides B, we write it like this, and we read it A divides B, of course. And we can also say that A is a factor of B and B is divisible by A. Now we will look at theorem 2.2.2. That is, let A, B, and C be integers. If A divides B and B divides C, then A divides C. This is going to be a simple proof. This is going to be another example of a direct proof. So let me write this down. Let A, B, C be integers. And then we know that A divides B and B divides C, and then A divides C. This is actually the transitivity. We call this property transitivity. So if a property holds for A to B and B to C, then it holds from A to C. We call this property transitivity. You'll learn it later. So our assumption part is this, and our conclusion part is this. So let's begin with our assumption part. So let me write here, proof. By basic rules of argumentation, I would say assume the given, or let me write it down. Assume A, B, and C belong to the integers, and A divides B, and B divides C. Then we know by divisibility, give me a second. Okay, then we know by divisibility that, give me a second again. Okay, so A divides B and B divides C. So we can write this as B is equal to A times K for some integer K. And C is equal to B times L for some integer L. But then, since we know B is equal to A times K, we can substitute the value of B. We can substitute the value of B, substitute the value of B, obtaining C is equal to A times K times L, which is equal to, since we know that multiplication is associative, and associativity is this property of changing brackets. So, like, example of associativity would be 2 plus 3 plus 4. If we're doing this, we can say that this is the same as 2 plus 3 plus 4. With this, if you can switch brackets in this place, or you can perform the operation in any order, like perform any of these operations first. If the answer does not change, then we can say that this operation is associative. So this is associativity. And since we know that the integer multiplication is associative, we can say that C is equal to A times KL. Now, we know that since K and L are integers, K times L is also an integer. Hence, A divides C. So we are done. Again, we took our assumption. This part was our assumption. And then we did some argumentation. Over here, this is our argumentation. And this is all based on stuff we already know is true. And the techniques we use in in the kind of in the form of mathematics we were talking about, and then we got to the conclusion. So this is another example of a direct proof. Did everyone understand this?
Yeah.
Okay. Any integer divides 0. Now, let's look at this. Now, this is an important part in mathematics, and you will see why this is important, because a lot of times the method you want to do your proof with does not exactly come to your head. You have to do a lot of rough work. You have to do a lot of mistakes before you realize how you will actually do your proof. So in mathematics, proofs can be extremely simple, but rough work can be extremely toiling. So look at this. Any integer divides 0. In the statement of this theorem, we're not given any particular choices of variables. In contrast to the previous theorem, which was stated in terms of A, B, and C. To prove something with about any possible integer, we pick an arbitrary one, say n. And then we need to show that n divides 0. It would certainly not suffice to choose any particular number, say 5, and then show that 5 divides 0, because this is not arbitrary. 5 is an arbitrary integer, but it does not represent all arbitrary integers. When we're trying to prove something that is true for everything, we try to take something that represents all arbitrary integers, not just one arbitrary integer. Now, once we have chosen an arbitrary n, the rest of the details in this proof are extremely simple. So let n be an integer. Observe that n times 0 is equal to 0. So there exists an integer such that you multiply that with n and you get 0. So n divides 0. So also, now people might say that this is a bit confusing, but with the domains and the definitions given to us, this holds. And as a mathematician, you don't usually question the domains given to you. You don't question the definitions and the axioms given to you. A mathematician's job is to do this. Take the definitions and the axioms and get whatever result you can out of it. So let's do some exercises. I don't want to outline the strategy. I will just go on with doing some of the important problems. Let's do exercise 2.2.5. Because this sounds. Oh, by the way, guys, from this exercise section, is there any problems that you would want me to do? So if there is such a problem, I would do that first and move on to the next part, because I'm only doing one exercise from this section. Anyone? Anything? So I believe not. Okay. So let's just do this, exercise 2.2.5. Arif, I believe you said that we can go to exercise if everyone is okay. We are at exercises. So Okay, actually, let's take the question. What is the question, Emily?
Yeah, I want to ask about the universal, how generalization, existential, instantation, those things.
Okay.
Yeah, yeah, we didn't mention it in on the lessons, so I don't know anything about them.
Universal instantiation and generalization, and
Yes,
existential instantiation and generalization.
yes.
Right? Oh, okay. So let's do that. Let's talk about universal instantiation and and existential instantiation. Instantiation. Now, if you learn quantifiers, we have two kinds of quantifiers. So there is for all, and we have there exists. Generally, we like to let's say U is our the set of all elements of all elements. Then we like to write our statement. So let's say P is a statement about X. We like to write our statement for all X belonging to U, PX. Or there exists X belonging to U, QX. And this is not a logical connector. I'm just giving examples here. So when we have statements like this, how do you do an argument with these statements? So we use universal instantiation. So where we would write something like this. So PA for PA, okay, and we'd say universal instantiation and this statement. So universal instantiation. Now, what does this mean? It just means that A is an arbitrary element from U. It's writing this, but in this form. Okay, as an example in the proof, we chose n as an arbitrary integer because we're not writing arbitrary integer everywhere. And over here we can say QB by existential instantiation. Now, what is the difference between universal instantiation and existential instantiation? This can switch value to anything. So if we have PA where we got A using universal instantiation, this can also imply PB because this is an arbitrary A and this is a specific B. So we can say PB. And this tool is useful because we can have different statements with different types of quantifiers. So first we like to quantify something that is existential, something that is specific, and then we use that same specific value for the all statement. So let me try to do a very simple example argument here. So let's say we're given for all X belonging to the universe, Px implies if Px, then Qx. This is our first statement. And then we have there exists X in U such that Px. And we want to get there exists X in U such that QX. So now you see that this is something similar to modus ponens, I believe. It's similar to if P then Q and P implies Q. Now, how do we do this? So let's say that this is our statement 1, this is our statement 2. From statement 2, we get statement 3, that is PA. And since this is an existential quantifier, we can say that we got this A by existential instantiation, by number 2 and existential instantiation. And once you get this, we can go to 4. We can say, now over here we have a for all statement, right? So this is true for any arbitrary x in the set of elements. So we can, since it's true for arbitrary elements in U, we know that it's also true for a specific element A in U. So we can say that we have PA implies QA by 3 and universal instantiation. And okay, now the key part of understanding this is I can do this from here to here. Like I can choose the existential part and then use that element in the universal part. But I cannot choose an element in the universal part and use it in an existential part because we don't know if they're going to be the same. Similarly, if this was also an existential quantifier, we could not say if PA then QA, because A is a specific element, and if this statement was also true for specific elements, we don't know if they're the same. But since this is specific, and we chose that this A to represent those specific elements, we know that A belongs in this set. We can use universal instantiation to say that this statement is true for A. Then we get from 4 and 5 n modus ponens QA by 4 and 5 and modus ponens. Now notice, now let's talk about generalization. What kind of element is A? A is a specific element, right? It does not represent all arbitrary elements in U. So we have to write, there exists X in U, that is just, there's some specific X in U, such that Q of X is true. And hence, we have gotten our argument. So this was done by number 5, and existential instantiation. On the other hand, if this statement was for all X in U, we could say that this is P of A and by universal instantiation. So A would be arbitrary, and we use the same A here by universal instantiation. So A is again arbitrary, and again here it will be arbitrary. So if this statement was for all, we can say that for all X in U, QX is true. And then that would be universal generalization. Sorry, generalization, I mean. Okay, so you get the idea, right? Is this hard to follow? Is there some part you want me to explain?
I get it. Yeah, thanks.
Okay, no problem. So I would suggest you go ahead and do some of these problems and try to derive a few statements yourself, and you get the hang of it. It's not that complicated. Okay. Next, do you want me to continue with proofs?
Yeah, yeah.
Okay, so let's do another example of a direct proof. So n and m are integers, and suppose that n and m are divisible by 3. Prove that n plus m is also divisible by 3, and n times m is divisible by 3. So I'll do the first part with this. So proof for the first part, and the second part I'd leave it up to you. So anyone here, how should we go about this? You can turn on your microphone and speak.
We can suppose that there is some integer for n that when we divide it, we get like let's say some a, that n equals 3a, and m equals like some b, 3b.
Okay. So
we can compare it with.
We can do that. So, but again, first, especially you're doing 1-1-1. Like later in mathematics, you don't have to write, but first you have to write your assumptions. So let's n and m being integers.
Okay.
Can I say some little thing? Maybe Emil said the same thing. Can we say that n is equal to 2k and m is equal to 2l, then m plus m 2k plus 3k plus 3l, and 3 in a parenthesis k plus l, then m plus m is divisible by 3. Can we do like this?
Yeah. We will do exactly the same thing, and I believe Emil was also suggesting the same thing.
Okay.
But first, you have to write your assumption, especially because you're in 1-1-1. It's very important. You will lose points if you do not do this. So let m and n be integers, and n. So 3 divides n, and 3 divides. Okay, it will end in 5 minutes. Let me finish this real quick. And 3 divides m. So as you suggested, so n is equal to 3 times a, and m is equal to 3 times b. Hence, by adding the two expressions, we obtain n plus m is equal to 3a plus 3b, which is equal to 3 times a plus b by the distributive property. Since a and b are integers, we know a plus b is also an integer. Therefore, 3 divides n plus m. And the proof for multiplication is also similar. So I believe you can do it by yourself because we don't have much time left. And I guess that's it for this meeting. I do not want to start a meeting again after this hour because I'm busy doing something else. But we can have another meeting tomorrow and we can continue with the contrapositive and contradiction techniques. Would that be okay?
That would be great.
Yeah. And did you understand everything we did here? Was it okay? Was it as good as the class, or was it okay?
I think it's this one is better than the class.
Thank you. Okay. Do you have any other questions? No problem.
Are there any questions from the past papers related to this lesson, or it's like?
Probably there are. Probably there are, but we can do them later once I'm done with all the techniques. Because since you said the lessons are not good, I'm not sure how well you understand the techniques. And this is a
I worked for the last years and the boss, no,
Yeah, go ahead.
maybe last year midterm too, we can find.
Okay, yeah, we will find. I will look at them. But generally, you can also do this. You will continue using these proving techniques: direct proof, contrapositive, contradiction, and later you will see equivalent statements, and you'll keep using them until the very end. So you'll use this with set theory, and then you'll use this in calculus, and you'll use this all the way up to your 4th year. So don't worry about it. There's a lot of examples you can take from. But right now, the examples in the textbooks will be good enough. Anyway, I will end the meeting now. I hope you had a good time. See you later.
Goodbye. Thank you for the lesson.
Bye, thank you.